Welcome to today's part of this SPSS methodology, this time with a unit on linear regression. We use linear regression analysis when we know that there exists a causal effect between at least two variables. So to speak more generally, we always have a dependent variable and a list between 0 and whatever independent variables which impact our dependent variable. And as I said, we need to assure that the independent influence the dependent, but the dependent is not influenced by dependent variable. So it's only like a one-way causal effect. Okay, so far for this. We also need to assure that our dependent variable is a metric variable and our independent variables are either metric or are so-called dummy variables, meaning they are 0-1 variables, 1 in all the cases that some specific characteristic comes true and 0 in all the other cases. So if we, for example, take a look here at our gender variable, we have 0 and 1. The 0 in this case would be like a base category, and instead of calling the sex or gender, we could call the same variable female or woman. Then it's like 1 for yes, it's a woman, and 0 for no, it's not a woman. So this is a variable we can introduce. However, marital status, here I have more than 0 and 1, more than 2 possibilities, so this variable cannot be introduced into our regression model. Not in the version as it here. This variable could be transformed or recoded, and then it might be used, but not in its pure form. Same applies, for example, here to the postal codes. Postal codes, they are, even if we think about this, they are numbers, but they're still nominal. Because a postal code doesn't mean that, well, if it's a 3, it's more postal code or more region or whatever, then it's 1. So it cannot be ordered sensibly, so meaning it's nominal. So something like this we cannot include into our model. However, gender, sex, we can include. With this in mind, we can then turn on how to actually can we do something like this in SPSS. So we go to Analyze. Here we have the point regression, and with this as well linear. So this is for linear regression. If we click here, we see there's space for one dependent variable. In this case, let's try to explain or assume that spendings on fashion and clothing can be explained via someone's age, gender, and income. And consider those 3 independent variables. In this first step, we do not go into any details, any additional options to activate. We just click OK and get here the results for our regression analysis. And the first part, first interesting aspect for us, are here the coefficients. The coefficients in this case can be interpreted in this way, that the constant, well, not always can the constant decently be explained. In this case means if all the other variables were 0, then the dependent would take this value. So here it actually makes sense. We could say if sex would be 0, age would be 0, income would be 0, someone would still spend around 41.21 euros on fashion and clothing. As I said, this is not as easy in all cases to be interpreted, in particular if there would have been like a value of -10 or something like this. So always be skeptical about interpreting the constant. However, all the other three variables here, their coefficients, they can sensibly be interpreted. Let's start with age and income first, so with the two metric variables. Age increases in steps of 1 year. So we could say for each year that someone becomes older, following this argumentation, he or she will spend roughly 0.041 euros, so roughly 4 cents, more on fashion and clothing. This is for age. For income, income measured in euros. So for each euro we earn more, we would spend roughly 0.017 euros on fashion and clothing. So roughly 1.7 cents. Or in other words, this tells us we would spend roughly 1.7% of our income on fashion and clothing. Okay, this is easily done and easily understood, but what about here sex? This was 1 for women, 0 for men. So we can't say the more female the person is, the higher, or for each unit more female, it's 24.26 euros more. But we can say the 1 category as compared to the 0 category, so in our example the women compared to the men spent 24.26 euros more on fashion and clothing. So if we use a dummy variable, the coefficient can always be interpreted as the 1 category as compared to the baseline as compared to the 0 category is by this much larger, or if it were negative, by this much smaller than it would have been for the baseline category. So here women spend more on fashion and clothing than men. Okay, so we have 3 different variables with 3 different signs. As we can see here, gender has the largest impact in this case, age the second, income the third one. But then we need to take care because they are all 3 measured on different scales. So if we want to get rid of the scales and compare them without having any scales or measure them in the same way, we could turn to the standardized coefficients. Standardization also gets rid of the scale level. And there we see the most important aspect, still our gender variable. The second most important, however, that's income. That's like half of what gender makes, and it's more or less 10 times as important as age. So age is the least important aspect regarding spendings on fashion and clothing. We can also test something like this. If we turn here to the t-test, or the t-values, which basically result from unstandardized coefficient divided by its standard error, we can take a look what the corresponding significance level would be. Then we can see as this value and that value are smaller than 5%, that sex and income have a significant impact on spendings on fashion and clothing, but age with 70.8% is clearly larger than 5%, so age does not have a significant impact on fashion and clothing. This could also be interpreted differently, that we can say for sex and income the coefficient is clearly different from 0. However, with age, this could also be 0. This could just be a random fluctuation leading for this year to be a value different from 0, because the standard error is so high, at least compared to the coefficient. This is a problem, and this means that, well, age basically has no real impact on spendings on fashion and clothing. Well, in other words, means we could also exclude age from our observations, from our model. We will do something like this in the next step, but first off we turn to the tables above here. We covered the idea how to interpret the coefficients. We also covered the idea how can we find out which of the variables actually contributes to our model and which doesn't, like 8. But what about the quality of the model as such, about the whole model? That's where here the R squared and the ANOVA with the F-test comes into play. The R squared tells us how much of the deviation of the variance of the dependent variable can be explained by using our 3 independent variables. And then we see here in this model we can explain roughly 11.6% of the deviation or of the variance of our dependent variable. This might sound a lot for some, but for most would sound rather little. So it might make sense that we test whether this model actually can explain a significant amount of this deviation. And for this we turn to variance analysis, because there the question was basically the same. We wanted to know whether the grouping actually explains a significant amount of the variance in the dependent. So here we run as well an ANOVA, perform an F-test, and if this F-test turns out significant, so if this F-test reports a significance level of less than 5%, which it does here, it can be said that using this model we can explain a significant amount of variance. So this might seem small, but it's still a significant amount. However, if we would like to use this model later on to do some kind of predictions, then this clearly is not suited, because we can only explain roughly more than 11.6%. So this tells us this is a significant amount, but this also tells us this model is clearly not suited for predictions. So this F-test allows us to do some additional, or get some additional insights on the quality of our model. So then we're only left with like 2 things to go, because we can easily test for 2 other significant problems in our data, which is autocorrelation. Autocorrelation here is not this important, because in this case we do not have time series data. Still, autocorrelation can happen, for example in the case of spatial autocorrelation, but it's usually not this severe a problem as with time series data. The second part, which is clearly way more important, way more critical, that's multicollinearity. So we're going to test for both of them. We can also easily do this by returning to regression, linear, then go here to statistics and check once the Durbin-Watson and secondly the collinearity diagnostics. This is on autocorrelation, this is on collinearity, multicollinearity. So we click on continue and OK, and we see we get, well, some more tables down here, but we are way happy that needs to be with this statistic and those 2 columns. So in particular here we have the Durbin-Watson statistic. This statistic needs to be as close to 2 as possible. So here we have a value of 1.995, so basically it couldn't be better. So we clearly do not have any problem with autocorrelation whatsoever. So this taken care of, we can turn our glance down here to the collinearity statistics, to the tolerance and the variance inflation factors. They are basically opposites of each other. So tolerance is like VIF, or 1 divided by VIF. Meaning, We have a critical value for the VIFs of 10. If you get a VIF larger than 10, should directly erase this variable, omit this variable from your regression analysis. So same applies for tolerance. If the tolerance is less than 0.1, erase it from your model. However, I personally would recommend to start becoming critical, or start thinking critically about your data when you see that there's a VIF of 2, larger than 2, or correspondingly a tolerance level of less than 1/2. Here we see that's the case for age and income. Well, let's start thinking critically for a moment. Then we might come up with the explanation that if someone is older, usually due to more experience, he also earns more. So the two independent variables, age and income, actually are not independent. They might impact each other. So in this case, we should drop one of the two variables. Well, luckily, here we see age is insignificant, so it would make sense to drop age nonetheless. If this would not be the case, I would go with select the one with the smallest standardized coefficient. Still here, it's also the smallest standardized coefficient, so in the next part we will erase our age variable. Before we do this, however, please recall here the F value of around 44, our R squared of 11.6%, and the adjusted R square, which is basically the R squared, but cleaned up for the number of variables, number of independents. Meaning, if ever we add an additional independent variable, R squared can only increase. We can only explain more of our variance. So the adjusted R squared considers whether each new variable actually really contributes to the explaining of the variance of the dependent or not. So this takes care of the number of variance. So with this in mind, we return to our command regression linear and we omit age. We see here R squared stays the same, adjusted R squared increases, F value increases. F value increases by roughly 1/2. So it's a significant increase. And our variance inflation factors are close to 1. They are close to 1. So we got rid of our problem with multicollinearity. Durbin-Watson still close to 2, so no problem with autocorrelation as well. So this then would be our final result for the model. A model which can explain a significant share of the variance in the dependent, where we do not have any problem with autocorrelation, and where we do not have any problem with multicollinearity. All of the two impact factors are highly significant, so they each contribute quite something to the explanatory power. This then would be like the rough part on linear regression analysis, and I hope you enjoyed listening to it and learned at least something from it. If you want to see more of this type of explanatory videos, feel free to visit the rest of this SPSS methodology. So until then, see you and goodbye.